Okay, so let's look at the proof of the fundamental theorem of differential geometry, or I guess the fundamental theorem of Riemannian geometry, which is that on any Riemannian manifold M, G, there is a unique Levi-Civita connection. So a connection which is compatible with the metric, i.e. the parallel transport structure actually determines an isometry of the inner product spaces rather than just an isometry of the tangent spaces, as well as this torsion-free condition, which is equivalent to the torsion-free condition, just double check here, is equivalent to requiring the Hessian is symmetric. Sorry. So yeah, Hessian is symmetric, and then the metric is parallel. So torsion-free and compatible with the metric. Okay, so the proof of the uniqueness of the Levi-Civita connection. Okay, uniqueness and existence are proved in one foul swoop in coordinates. Okay, so essentially, we know that since we know that we choose a coordinate system, and we know that the Christoffel symbols of the connection are going to be symmetric in the bottom two indices. Okay, so then we can go ahead and start taking derivatives of the metric. So when you take the derivative of the metric here, so go ahead and take the derivative of the metric, and I'll just zoom out so you can pause the video here if you want. If you want to do so. Anyways, we'd start taking the derivative of the metric. Okay, so partial I of g jk is partial I of g evaluated on partial j partial k, and then we're going to use the metric compatibility here and here. Boom and boom. Okay, so with this step we invoke the metric compatibility, and then we just use the definition of the Christoffel symbols here to replace these covariant derivatives with their Christoffel symbols. We're working in coordinates, and then of course these Christoffel symbols pop out of the metric because it's bilinear, so we end up with this final expression here for the partial derivative of the metric with respect to partial I g j k. Now to perform this, we permute the indices. Okay, we permute the indices essentially, form the cyclic permutations of the indices to get different expressions, and then we use the fact that these Christoffel symbols are symmetric in the bottom two indices to essentially take these partial derivatives of the metric and their permuted indice forms, and we add them together in this way. So we add together two and then subtract the third permutation, and we end up with just a single Christoffel symbol multiplied by the metric here. So then we can just multiply by the inverse of the metric to solve for the Christoffel symbols. And so you can see that the Christoffel symbols are uniquely determined by the metric. These are the, again, we crucially used metric compatibility in this step here. Sorry, not in this step. In the very first step to evaluate this partial derivative, we used metric compatibility, and then we used the torsion-free property, which is equivalent to requiring the Christoffel symbols are symmetric in the bottom two indices, to go ahead and add two of the permutations and then subtract the third, and end up with an explicit, so taking the inverse of the metric, we get an explicit equation for the Christoffel symbols in terms of the metric. Okay, it proves uniqueness because, again, the Christoffel symbols fully determine the connection, they characterize the connection, and so we have them fully characterized by the metric. Okay, so that proves this in coordinates. Okay, but there is also a coordinate-free proof. Okay, so let's proof. Okay, all right. So again, we start off with this inner product of nabla xy comma z. Okay, we use the fact that we have metric compatibility to expand this in terms of the product rule. Then we use the torsion-free aspect to replace this nabla xz with nabla zx, and then plus the commutator of x and z. Okay, and then we go ahead and repeat. So notice how we used the metric compatibility, and then the torsion-free property. And we're going to repeat this over and over again. Okay, so now we go to this expression, inner product of y with nabla zx. We replace that using the replace this with z of y comma x minus, essentially in parentheses, minus inner product of nabla zy comma x. That's again using the metric compatibility. Then we use the torsion free to replace this nabla zy with nabla yz, and then bracket here, and we just repeat this process. Now we do it again for nabla yz. We do this again. We use the metric compatibility, and then we go ahead and identify, okay, nabla yx. Now we're going to use the replace nabla yx with nabla xy plus inner product, Lie bracket y comma x. Okay. So again, this is now torsion free property. Is that the correct? Might be a missing minus sign here. Does that look right? Oh yeah, that's right. The minus sign is just getting thrown into this Lie bracket here. Okay. So finally, essentially, we've used in turn, we've used metric compatibility, torsion-free, metric compatibility, torsion-free, metric compatibility, torsion-free, to basically move around this covariant derivative nabla xy until we finally get another nabla xy here. And then we can add this over and solve for this inner product of nabla xy comma z explicitly just in terms of the inner product, so the metric, and these Lie brackets. Okay, so we have an explicit formula, namely 2 times the inner product of nabla xy comma z is equal to the following expression, which I'm not going to repeat out loud, but the important point is that this expression is only determined by the inner product, basically, by the metric. Okay, so it's fully determined by the metric. So that tells us that, well, this covariant derivative, nabla xy, this vector field, is uniquely determined by the metric. Okay, and since z was arbitrary, we could determine that this affine connection in general is just entirely determined by the metric, and we can define it to be, we can take this to be the definition, actually, and this is called the Kozul formula. I cannot pronounce this. Koszul formula. Okay, and so yeah, this proves existence and uniqueness because we've come up with an explicit formula. So we've literally constructed the formula for the connection. Okay, we've characterized that connection and constructed it entirely in terms of the metric. And so not only did we prove it exists by constructing it, but this construction, every step, was essentially unique because there was only the equality must hold. If we've assumed metric compatibility and torsion free, then the equality must hold, and so we're going to get again this Levi-Civita connection uniquely determined by the metric. Okay. The last thing I want to mention is the proof. One thing we kind of skipped over is the proof of this this proposition 2.1, that if you have a linear connection, then the parallel transports being isometries of the inner product spaces is equivalent to the more traditional characterization of the metric compatibility, namely this product rule here in terms of the covariant derivative. And the product rule in terms of the covariant derivative is like directly equivalent to just requiring that G is parallel. If you use the definition of the covariant derivative induced on the tensor, then this equation here, if you subtract over the left-hand side, this equation is literally nabla x of g of yz. So requiring that this is equal to 0 is equivalent to requiring this metric compatibility property in terms of the vector fields. But the equivalence of 1 and 2 is somewhat non-trivial, and the key proof relies upon taking an orthonormal basis of the tangent space, and then orthonormal basis is parallel transported along a curve. And the key insight to the proof is that if the orthonormal basis remains orthonormal as it's parallel transported, then you're going to get the parallel transport maps are isometries, okay? And this part 2, okay? So just look at this proof here. If we look at the parallel transport, so fix an orthonormal basis at the E sub I, an orthonormal basis at a point P of gamma of 0, and then parallel transport the basis along gamma. If we take the derivative of the inner product of two of these orthonormal basis vectors as they're being parallel transported, okay, we look at the derivative of this inner product, then we recognize, okay, this is just the directional derivative in the direction gamma prime of the inner product of EI and EJ, and then we can then use metric compatibility, expand this in terms of the product rule, okay, and then by definition these are being parallel transported, so their covariant derivative in the direction gamma prime is 0. So in particular, we're going to end up with this expression equals 0 because these vectors EI of t are being parallel transported. So what that means is that the inner product between these orthonormal basis vectors is unchanging. As this orthonormal basis is parallel transported along the curve, it remains orthonormal. Okay, and that is basically an equivalent condition to check that in fact these parallel transport maps between the tangent space at gamma of 0 and the tangent space at gamma of t actually preserve the inner product. Okay, so they're not only vector space isomorphisms, but they're isometries. They preserve the inner product. Okay. All right, let's see. Did I miss anything important? I don't think so. I think we covered everything in a very hand-wavy, or like a very dragged-out way. But hopefully this is somewhat helpful. Have a nice day.